Okay, let me recall. Yesterday I tried to give some motivation for why you would want to have a definition of Motivic cohomology, and maybe also why you would want to compute it. And I mentioned some of the things we know about Motivic cohomology. And let me draw one of those charts so we can see which Motivic cohomology groups we know and which we don't know. So we have these two indices, right? So we have hi of x zj. And let me remind you again that I said yesterday that the general formalism of these motivic so categories of triangulated categories of motives allows to relate Motivic cohomology over schemes with Motivic cohomology over fields. And so for the purposes of this lecture series here, I want to concentrate mostly on the field case. Okay, but we have two indices, so we can write this in a plane. And so one thing here would be the coordinate I, which would be the cohomological degree. And here we have J, which we can think of as weight. And then what do we have? So let me write it like this here. So we have H0, 0. This is the integers. And here the rest of this is weight 0, would all be 0. I mentioned the identification of the cycle complex Z of 1 with sheaf of units shifted by -1. And that means that we also know pretty well what the first row is here. We have zeros here, and we have a 0 here, and then we have the units in H11. I should take care of that my O looks different from the zeros. So O star of X, if we're talking about the scheme X here, and then we have the Picard group here, and then zeros there. So I mentioned that we have something about, so the identification with Milnor K-theory is that Hn of, well, let's say in the field case we have Hn of Fn is isomorphic to the Milnor Kn of the field F. And that would be roughly this line I equal to J here. So we would, if we're talking about a field, would find the Milnor K-theory on this line. And then we also had this thing that H2n of xn, these are the ordinary Chow groups of X. Those would live on something like this line, I equals 2J. And then vanishing statements I mentioned yesterday would imply in particular that to the right of this line I equal to J, everything vanishes. There's no Motivic cohomology there. The refined vanishing that you get out of Zariski-Onisnevich cohomological dimension statements mean that if we're talking about fields, everything to the right of the line I equals J vanishes. Right, everything to the right of this line, Motivic cohomology would be 0. Okay, so this basically summarizes what we have here. So let me say at this point we would have like Milnor K2 of the field, and I mentioned that one of the interesting, should put it up here. So so in this H2. And one of the interesting cohomology groups that appears and about which we already have open questions which we can't answer at this point is K3 indecomposable, H1 Z2. So that should be a short summary of what we know and some of the things I talked about yesterday. And the next point would be open questions and why we want answers. So of course you can ask all sorts of questions, but I mean the questions that I mentioned, I mean they're asked for a reason because they would have interesting implications. One of the first things is, well, notation suggests that we want to think of this as a cohomology theory, and typically cohomology theories, like ordinary cohomology theories in topological spaces, vanish in negative degrees. And this is the first and one of the major open questions that you can ask. So we have no idea at this point what happens above here, but we would expect that it's 0. And this is made precise by the Beilinson-Soulé vanishing conjecture. So I mentioned some vanishing results yesterday already. This is sort of to the right of this. And the more, so I mean, these come out of the formalism, and the more complicated things that do not come out of the formalism, and well, every case in which we actually know these conjectures is very difficult to establish. This is the vanishing to the left of the J coordinate axis. So we expect that Motivic cohomology, and this is also a statement that's not quite specific about fields. And this is really, you can ask this for schemes. And you would really like to think of this as a cohomology theory. So this should be 0 in the case where J is greater or equal than 0 and I is less than 0. I mean, the J greater or equal 0 isn't really relevant point. The relevant point is that if I, the cohomological degree, is less than 0, this should all vanish. And this concerns this quadrant here. And there's a refined statement. We would also want that we get a vanishing for when J is greater than 0 and I is equal to 0. So if J and I are 0, we know that we have a Z here, but the expectation in this refined part here is that also on this J line here, we should have zeros. I guess here we know it, but here we don't. Right, so maybe informally, of course, this is one of the this is the reason for formulating it. You expect that this HI of XCJ really behaves like an ordinary cohomology. Theory. But it's not just that we would expect that these things behave because we want the things to be so close to topology. This conjecture also would have several significant implications. Say it has a number of nice consequences. such as the existence of an abelian category of mixed state motives. And I'll say something about this shortly, right? Because you remember the goal was to formulate some alternative complexes which compute Motivic cohomology, and in one of the setups that I'll discuss, the Bellington-Soulet conjecture actually plays an important role, because then we get some abelian category of mixed state motives and a Motivic Galois group, and then sort of cohomology of this Motivic Galois group should give Motivic complex, computing Motivic homology with rational coefficients. Okay, so
why only take part? I mean, I don't think there is some solution it is mixed. I mean, category mixed motives, no?
I don't. No, I don't think so. The reason here is if we look at the category of mixed state motives, then essentially morphisms between these things can be reduced to K-theory or Motivic cohomology, because of the formula that I mentioned yesterday, that this can actually be computed as hom from Z to Z J I. So Motivic cohomology controls morphisms between mixed state motives. And this is why you get, then statements about abelian categories of mixed state motives, because you can control these morphisms. I'm not sure that we would, I have no idea what morphisms between, like, what's the morphism between a motive of a K3 surface to some other thing. I don't think we have precise identifications. And then, so this is really just restricted to the setting of mixed state motives. Yeah.
Can you say how the thing is how the simplification works in the Finiteness Conjecture, how you get the abelian categories?
Yes, this is going to be the next paragraph. Sorry, this is probably disturbing the microphone. It's always clicking. At least I'm disturbed by this. I gave a knot theory seminar last winter. Okay, ready to go. So maybe I mention one more thing, that this is known for F a finite or a global field. Because in these cases we can actually compute rationally the K-theory, by reducing to group homology computations, and so in these cases we know that everything works, and all the other cases, I'm not sure if anyone has an idea how to approach this. Okay. So this is one of the conjectures. Motivic cohomology should behave like a cohomology theory, so some of the negative cohomology groups should vanish. And then there is another conjecture that concerns the next bit here. This line, which in particular, so this is not an issue for O star, because in weight 1 we basically know everything we want to know, but this is already a conjecture open for K3 indecomposable. That's called the rigidity conjecture. And here, I'm not quite sure what the proper attribution should be, because whenever it appears actually stated in a paper, it's attributed to someone else. And then I couldn't find the original source. But in various sources, this is attributed sometimes to Beilinson, sometimes to Suslin, or Merkurjev-Suslin. I actually also found a source attributing it to Saar. It's a very natural conjecture, and probably any of these names, any of these people were aware of the importance of the conjecture. So rigidity is a statement about H1, so the first Motivic cohomology. Namely, let me formulate it like this. So we take K into L an inclusion of algebraically closed fields. Then there is a natural map of Motivic cohomology. Namely, we go from H1 of the spectrum of K with Qn coefficients to H1 of spec L with Qn coefficients. I guess what we already know from general nonsense is that this is a split injection. But the conjecture asks that this is an isomorphism. For n greater or equal 2. For n equal 1, this is obviously false, because you have the units here. But the expectation is that for all the higher weights, it should actually be an isomorphism. So, and this is already an issue for K3 indecomposable. This is the first case where we don't know this conjecture. And this is H1Z2. Why would this be interesting? One of the interesting cases is, at this point we don't know what H1 spec of the complex numbers with Q2 is. However, we know, or at least, know in a specific sense of the word, what this Motivic cohomology for spec Q bar is. Let me mention, so in this is already hidden here, right? Borel computed the Motivic cohomology in terms of K-theory or group cohomology of number fields. So we know the ranks of the K groups, and we also know the ranks of the of H1 Z2 for number fields, and then we also know it for Q bar, and we know that basically this Motivic cohomology group is completely detected by the Borel regulator. So in a sense, we know this group. It's a countable dimensional vector space over Q, but we have explicit maps, namely the regulators that we can use to understand this thing. And we would like to say something about H1 spec C, Q2, but we can't at this moment. For all we know, this could be significantly bigger than the corresponding group for Q bar. And so why would we want to know what this is? Well, we should know Motivic cohomology of the complex numbers, because this is, for all other cases, usually the complex numbers are simpler than anything else, because you have all these analytic tools available, but in this case they actually don't help, right? Everything that you can see with analytic tools, regulators and so on, is the stuff that comes from Q bar. So so I mentioned this only now, why this conjecture in this case is interesting. I'll come back to this in the scissors congruence part. So this would imply a negative solution to the simplex problem. Which is a question, I guess, already asked by Schläfli, something like 150 years ago. If you take a three-dimensional simplex in the three-sphere, and you require that all the sides have angles which are just multiples of pi, is then the volume of the simplex a rational multiple of the sphere volume? And we don't know this. We would expect that there exist such rational simplices with irrational volumes, but we can't prove it. If we had this rigidity conjecture, we would get explicit examples of simplices that do have irrational volumes. So this is one of the things. This would have an implication which you don't need to know Motivic cohomology to formulate this consequence. And I think it's a fun consequence. It's really volumes in metric geometry. Yeah. Okay, so this is the second conjecture that I wanted to explain. So in these two conjectures sort of deal with all this part of the diagram. I'm not quite sure. Well. Yeah, okay, I'll say, so when I discuss Finiteness Conjecture, this also means something for the rest here, which we know, well, exists and can be non-trivial. So. Okay. Maybe some other type of conjecture. This is more arithmetic nature. Some other type of conjecture. Well.
What's the name of the conjecture in parentheses?
This one? Yeah. I think it's really called the rational simplex problem. Yeah. Okay, so we have finiteness conjectures. At this point, yeah, I'm leaving the world in which I made all these definitions, like working over fields. But these can be appropriately formulated. I mean, for K-theory, there's no problem, right? So there's Bass's finiteness conjecture that says, well, if X is a regular scheme of finite type over the integers, then its K-groups should be finally generated. Right, so that's conjecture about K-groups, and then, so historically, of course, you know that the K0 of Dedekind ring, or yeah, a number ring, let's say, is essentially the class group plus the integers, and K1 is the group of units, and classical number theoretic results tell us that these things are finally generated. And so this is a natural generalization, well, both to a higher K-theory and more general schemes. So numberings would just be sort of relative dimension 0 over the integers. There is a refined version which you can find in papers of Geisser and Kahn, which then claims, okay, Motivic cohomology should also, this should be finally generated. Well, here it should of course mean for all I, here it should mean for all I and j in this situation that we look at a regular scheme of finite type over the integers. Right, so let's not worry really about how to define these things. And one of the things that I can say is that we know this. Yeah, let's say dimension 1. Right? So dimension 1 means this can either be a number ring, or it can be the ring of functions on a curve over a finite field. Right, in this case, so for K0 and K1, this would be classical Dirichlet proved all these things, mostly. And then the higher K theory, this is Quillen.
Surface of a finite number, of a finite field, we don't know finiteness of K.
I think that's true, yes. We don't know it for surfaces. If we knew it for surfaces over finite fields, yeah, I mean, this would already tell you something about K theory of like elliptic curves over function fields and positive characteristic. And yeah, that's not known at this point. Okay, so yeah, so why believe finiteness conjectures? Well, the motivation is, of course, that we know this thing in dimension 1 and would then expect that it holds in higher dimensions. Maybe something that I should would like to mention at this point is that we have an implication here that you can also find in papers on these kinds of finiteness conjectures by Geisler and Kahn. If we had these finiteness conjectures, then we would get both the Beilinson-Soulé vanishing conjecture and the rigidity conjecture. Right. So how does this work? Let me sketch this very quickly here. If I assume that hi of x z j is finitely generated, then I can localize at any prime you want. So invert L, everything outside L in the coefficients here, and then you have the multiplication by L, and you get an exact sequence to Z mod L. And then the thing is, well, if we're really in the negative degrees, so if I is really negative, then all this Bloch-Kato and Beilinson-Lichtenbaum stuff tells us that at this point we would have actually étale cohomology, and that vanishes in negative degrees. So you know that this must be an isomorphism, but it's multiplication by L on something that is finally generated, and then it must be trivial. So this is one of the things that I alluded to yesterday. Now by all this work of Wawacki on Motivic cohomology, we know a lot about the finite coefficient case, and this is one of the things that allow us to deduce Beilinson-Soulé in this case here from finiteness assumptions on Motivic cohomology. Rigidity can also be deduced. It's essentially, well, if you look at, for instance, Motivic cohomology class over the complex numbers, by some sort of continuity argument, this would always come from, it would always be supported on some variety that is of finite type over a number field, and then you can choose integral models and use these finiteness conjectures to show that the class should actually come from Q bar already. Right, so this finiteness conjecture, this is also one of the motivation. Of course, you have the number theoretic motivations. Well, you would expect that these things should be finite, and this is also a good motivation because it has, it implies all these, the vanishing conjecture and the rigidity. So in particular, if we knew finiteness for K3 things, that would also give a negative solution to the simplex problem. So if we can actually show that all simplices have rational volumes, then bus finiteness is wrong. Anyway, so there's one more conjecture I want to mention, which also helps, at least in producing lots of non-trivial elements here. and also makes very precise predictions on what the size of motivic cohomology groups should be. Which one? I'll take this one. So the statement of this next conjecture, I want to say something about one particular of the پ.L.Чебышева conjectures. Actually, the full statement would take far too long, and it requires talking about regulators, which I promised I wouldn't do. So I'll be very brief in the formulation. Let's say it's one of پ.Л.Чебышева's conjectures. So what we have is we can look at, what do I want? When X is a finite type of a number field, projective and regular. So then we have motivic cohomology. And so what П.Л.Чебышев considered was, well, you can look at a model X over the integers, assume that it's regular, then П.Л.Чебышев, I mean, this is very close to how you define motivic cohomology over for things which are only defined over the integers and so on. So what П.Л.Чебышев did is he constructed a subspace in here of things that should come from this model. Let me write it like this. And П.Л.Чебышев also constructed a regulator that goes to some version of the linear cohomology for X base change to R with Rn coefficients, and I really don't want to say anything about the definition and so on of this. But the thing is then you can compose these two things. You have sort of the motivic cohomology that comes from a regular model of X, and you can then look, so you can tensor this thing with R and then look at the map to the linear cohomology. This should be an isomorphism. And then there are all sorts of other conjectures telling us something in terms of this picture about how to relate L values, how to say something specific about L values of the variety in terms of motivic cohomology. But what I want to point out at this stage is the conjecture in particular says that some motivic cohomology group for some integral model here is isomorphic to something that is defined analytically and that can also be computed in relevant cases. And again, sort of if you believe this conjecture, this also implies П.Л.Чебышев vanishing and rigidity, basically because in the index range for П.Л.Чебышев vanishing, the Deligne cohomology groups vanish, and in the range for the rigidity, this essentially concerns sort of the algebraic fundamental group, so the algebraic closure of the prime field in the variety. And so this is, so also here you get some sort of rigidity statement for the Deligne cohomology that would then, via this isomorphism, transfer to motivic cohomology. So also П.Л.Чебышев's conjectures, so I mean, in particular this one on the ranks of motivic cohomology groups, imply these vanishing and rigidity conjectures. Okay, so this is a very conjectural picture, but I mean the statement is if we knew all that, we could already make a lot of statements about what motivic cohomology is. We could say, well, a lot of motivic cohomology groups and with the negative degrees vanish. We can understand H1 of H1 motivic cohomology because this is all coming from essentially number fields. And well, at least if we have this, we could also produce a lot of non-trivial elements in all the other motivic cohomology groups and actually show that for the complex numbers, they should actually be infinite dimensional vector spaces again. Okay, so this is the conjectural picture. And the next step now should be, I want to explain, if we assume these conjectures plus something more, then we get natural, I mean, well, natural. We get complexes computing motivic cohomology. And complexes look much more like, yeah, there's in some sense symbol presentations, like for Milnor K-theory you have this symbol presentation, and the complexes that come out, if you assume these conjectures and some more conjectures, then also have this kind of symbol presentation. Okay, so what's the next step? Motivic complexes via cobar resolutions. So yeah, I want to explain how conjecturally motivic complexes, so complexes computing motivic cohomology would look like. And this is so eventually the complexes that come up can be found in papers of Goncharov. But before I discuss this, I'll discuss how, if we know the vanishing, we get a billion categories of mixed tape motives, and that's work of Marc Levin. Well, I'll not actually explain how the proof works, but I'll explain some of the things that you have to do. Right, so what do we have? So we can start with these categories, triangulated categories of mixed, motives. Let me write here with Q. Everything for the rest of this bit, in this paragraph 1.6, will also always be with rational coefficients. So we have these categories of motives. As defined by Wolwatsky and as we've seen in Frédéric's talks. And in there, we can consider DMT of F, which would be the full triangulated subcategory generated by the Tate motives, Qn for all n, right? So this would be a derived category of mixed Tate motives. Yes.
Okay.
Yes.
No,
so n could be in the integers in particular.
Okay.
Right. So you recall that I had mentioned this formula that you can compute motivic cohomology as morphisms between mixed Tate motives, Q0 to Qn shifted by something, and this in particular means that you can also do the same computation in here. So morphisms in this DMT of F are essentially controlled by motivic cohomology. And right, what we can say about this is tensor triangulated, because you have Qn tensor Qm is isomorphic to Qn plus m. And yeah, it computes K-theory in the sense mentioned last time. Okay. Right, then what can be done? So I'm following basically Mark's papers, but I suppose this could also be formulated in terms of weight structures in the sense of Bondako in some way. So we define W less or equal n dmt of f as the full triangulated subcategory generated by Q minus m for m less or equal n. And that gives a sequence of inclusions. So here you have W less or equal n plus 1 dmt, W less or equal n dmt, and so on. And then you have a sort of truncation functor that goes from dmt to W less or equal n dmt of f, and that is adjoint to the inclusion. And then you can define W greater n by looking at a triangle. So you have W less or equal n of a motive maps to m. And then the triangle, complete this to a triangle, and that gives you W greater n of m. And then you can sort of take graded pieces for this weight filtration. And the eighth graded piece would be, this is given, so the weight A piece of the motive M is given by you compose the two truncations. So you take W less or equal n composed by W greater n minus 1 applied to M. Right. Oh yes, thank you. N. And then sort of the bit, let me write it as GRWN dmt of f. So those things that really are pure of weight n. This can be identified with a bounded derived category of Q vector spaces. Right, essentially because, well, hom from Qn to Qn is just, essentially it's hom Qn to Qn I. This is 0 if I is non-zero, and it's just Q if I is 0. And that's basically how you get this identification with the derived category of Q vector spaces. And then you have, can consider this functor H0 of this graded piece. And that goes from the mixed tape motives to Q vector spaces. And the theorem is then that you get a T-structure out of this by conditions on vanishing of this cohomology of the weight-graded pieces. And then sort of to verify that you have a T-structure, some morphism spaces should vanish, and this is exactly how you use the Bailenson-Soulé vanishing conjecture. So if Bailenson-Soulé holds over the field F, then we have two things here, dmt of F less or equal 0. This is those motives where Hn of GRAW of M is 0 for n greater 0 and all A. And similarly, we have dmt of F greater or equal 0, and there the condition is that Hn of GRWAM is 0 for n less than 0 and for all A. Right, the statement is that this is a T-structure. And the heart, this is mt of F, is dmt less equal 0 intersection with dmt greater equal 0. This is then an abelian category of mixed Tate motives. And it is generated in a sense by Qn, in the sense that the smallest triangulated subcategory, which is closed under extensions and contains the Q of n, will be exactly that.
In that case, the DMT would be the unbounded derived category of this abelian category.
Yes, in the case of Bailenson-Soulé vanishing, we can also say that.
I mean, your lemma, if Bailenson-Soulé holds down something, blah, 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 and we get the hearts an abelian category, and I'm just wondering if its derived category recovers DMT of F.
Yes.
Okay.
Yeah. So you can actually then compute Motivic cohomology as X groups between.
Okay. Okay.
This is known for number fields, finite fields and function fields of curves over finite fields.
Taking rational coefficient is important? Or
Yeah, I should think so. I'm not sure how much integral statements can be made there, but to be on the safe side, use rational coefficients. So, right, if we have the Bailenson-Soulé vanishing, then we get an abelian category of mixed Tate motives. We actually get more. We get that, well, this mt of F is Q linear abelian tensor category. Abelian comes out of this T structure business. Q linear is because we're working with Q coefficients. And we also get a tensor category because, I mean, I mentioned before that you get this, that we have a tensor structure and that's sort of inherited by the heart here. And that's also rigid, so basically you have a duality such that hom, so internal hom from A to B, can be expressed as a dual tensor B. Right? So then you have this Tanakian formalism. And this means that we get a Motivic Galois group. So this means that motives, let me say mixed Tate motives, are the representations of a pro-algebraic group, which we would call gal mod of F, Motivic Galois group. And we can say something more specific about this. We know what the structure is, so gal mod actually sits in an extension, well, a split extension. The quotient is the multiplicative group, and this is basically the weights stuff that is captured by this. And then we have U mod of F, which is a pro-unipotent group. So this is one of the things. The point is, so the next step is, because this is a pro-unipotent group, and so pro-unipotent you also get so from statements that you can make about maps between mixed Tate motives. So this thing here is determined by its Lie algebra. And this is called the Motivic Lie algebra. Let me say L mod of F. And well, so in the sense of Tanakian formalism, you know that this group arises as automorphisms of fiber functor. And here, fiber functor, you could use one of those things that we had before. You can either use a fiber functor like this, H0 of these graded pieces that goes to Q vector spaces, or you can just omit this and then you go to graded Q vector spaces, and that already sort of takes care of this. So the graded Q vector spaces would be representations of the GM, so you can take care of this as well. Right, and then in this picture, so the Galois group is obtained as automorphisms of the fiber functor. And the Lie algebra is, you can write down what are derivations on this fiber functor, and then you would get that this Lie algebra here is given as derivations of this fiber functor. So what's the point? Why are we talking about this? So if we have Beilinson-Soulé, we get an abelian category of mixed Tate motives, which is really just a category of representations of some, well, now you can choose what you want to say, of an algebraic group or representations of this Lie algebra. And because DMT is actually the derived category of this abelian category of motives, you can actually compute in this situation where we know Beilinson-Soulé. We can compute Motivic cohomology in terms of, well, as cohomology of this Motivic Lie algebra. With suitable coefficients. And this is what I meant. The title of the subsection was Motivic complexes as cobar resolutions. You know that there's this Chevalier-Eilenberg complex to compute the cohomology of a Lie algebra. right? And if we're now writing out the Chevalier-Allenberg complex for the motivic Lie algebra, we get a complex that computes motivic cohomology if we have all these situations, because the motivic cohomology is given as well, hom in the derived category, or then as X in the abelian category of motives, which is just representations of the Lie algebra. Okay, so what does this look like? Note also that all this, I mean, we had this weight stuff, and this actually, we have the weight stuff here. And this implies that we actually, this Lie algebra, or also the Hopf algebra for the Galois group, has a grading. And let me, the other way around. We have this Chevalier-Allenberg complex. The motivic Lie algebra has a grading, and this also gives a grading on the Chevalier-Allenberg complex. And the nth graded piece of the Chevalier-Allenberg complex for the Lie algebra computes motivic cohomology. And then this complex already from what we know, that we have a graded Lie algebra, we can write down something about this complex. You know that it's given essentially also in terms of exterior powers of the Lie algebra. And so we take the L mod F degree minus n, this, because sort of the way the morphisms go in the category of motives, you can only go from Q to Qn if n is positive. It eventually means that this Lie algebra sits in negative degrees. So we're talking about the negative degrees here. So we have the dual of the n, so minus n degree. And then here we have the dual of the, L mod F, degree minus 2, and the dual of that tensor with the exterior power of n minus 2, L mod F in degree minus 1, dual, and then last map goes to lambda n, L mod F dual minus 1.
Yes?
Yeah?
Is it dual in which sense?
And here we're just talking about Q vector spaces. Right, so and that is basically assuming valence and Soulet, we can compute motivic cohomology in terms of a Chevalier-Allenberg complex for the motivic Lie algebra. And that tells us already something about the form such a complex should have. We can be more specific if we throw in more conjectural statements. That's sort of will be the last thing I want to say here. So Goncharov has very specific conjectures what this Lie algebra should look like. Maybe I shouldn't clean this other board. So Goncharov has very specific conjectures about this Lie algebra. Well, you can write down something. We have this grading on this motivic Lie algebra, and we can look at those parts that are sitting in degrees less or equal minus 2. Right? Essentially, this is just throwing out L minus 1. And L minus 1 dual should be identified with the units in the field tensor Q. This is pretty much this GM factor that you get here, coming from coming from the GM factor. Okay, so we have this this subalgebra, and the conjecture is that this is a free graded Lie algebra. And the other thing is he has very specific conjectures about the nth graded piece of H1 of this Lie algebra I of f. So he has definitions of higher block groups. These things are defined as you take the free abelian group generated by P1 of f modulo an inductive set of relations coming from, well, essentially they should come from functional equations of polylogarithms. But let me say that even the definition of the groups requires that the rigidity conjecture for Motivic cohomology holds. Okay, so so Goncharov has these definitions of higher block groups and conjectures that the H1, the nth graded piece of this subalgebra I of f, is given in terms of this of these higher block groups, which in particular means that there's still the conjecture implicit in here that this definition of higher block groups works and so on. Yes, and now I still have to erase the board to actually write down the more precise version. So if this conjecture is true, we get actually a more precise form than the one I've written here for Motivic complexes, well, computing Motivic cohomology. So if this conjecture is true, then this is what Goncharov proves in his paper on Zagier's conjecture for zeta 3 already. Then the Hochschild-Serre spectral sequence. Oh. So if you have, here you have this ideal I of f, and it sits in the Motivic Lie algebra. And then you have a quotient, which is essentially L minus 1 there. And then for this extension, you have an associated Hochschild-Serre spectral sequence. And this spectral sequence degenerates to a complex, or let's say reduces to a complex, which has the form. So the nth graded piece, sorry, this is what we're computing here. So we have the nth block group, and then we have a differential going to the n minus 1th block group, tensor f star, bn minus 2 tensor, lambda 2 f star, and so on, until we get to b2 tensor lambda, so exterior power n minus 2 of f star, and finally we go to lambda n f star. So this is it. Right? If we have the Beilinson-Soulet vanishing conjecture, so that we can talk about the Motivic Lie algebra, and we have these more specific conjectures about the structure of the Motivic Lie algebra, then we get complexes here involving higher block groups, which compute Motivic cohomology in the sense that, well, this would be H1 of the field with Qn coefficients, this would be H2, and so on. In the end here, and I guess this is something that may actually be possible to show. You would get Milnor K theory, and here you would get the nth graded piece of K2 n minus 1. Okay. You can also make specific statements about what the differentials look like, but I'll not do that now. What's next is, so I've now told you assuming all sorts of interesting conjectures, we can write down very explicit complexes computing Motivic cohomology. And what I want to discuss next is complexes like this come up. So if we're talking about n equals 2 and n equals 3, you see complexes like this from group homology computations. And this is also where I'll then explain what a block group like B2 or B3 looks like actually in the presentation, because I haven't said anything about this here. So I'll explain how complexes like this arise, so at least for weights 2 and 3 in group homology. And then after that I'll explain how complexes like this appear in the discussion of scissors congruences and Dehn invariants. Okay, that's it.
About there is the vanishing of global fields. So does the vanishing hold integrally? So we know rational
Yes.
vanishing from.
Because of what we know about the finite coefficient things, the integral and the rational statements would be the same, also would be equivalent.
I see. So in general, rational vanishing.
Yeah.